And we are recording. So let me then hand the floor over to group number 3 to share your design with us.
All right, thank you all for being here. We are excited to present our heliostat module, Sunny Side Up, to you all. So we are group 3. We're consisted of Demir, William, myself, Colin, Joshua, Noah, and Shane. Can we get the next slide? Thank you. So for our hedgehog concept, we decided to focus on the simplest design. So in the beginning, we were struggling with, functionalities, different subsystems, how many we should have. And then we realized that if we focus on making the design as simple as possible, we could limit the part count, we could limit the manufacturing time and assembly costs. So the individual component complexity was minimized where possible. And an additional benefit is that there's easy maintenance over the lifetime of the module. So our design is made up of 3 subsystems: the structure, articulation, and optics. The structure is composed of those aluminum cross beams, the swivel. The articulation has those NEMA 23 stepper motors with neoprene belts and pulleys. And the optics is made up of a solar film on aluminum sheet metal. So an additional benefit of being this most simplest design is that we had a very small module area compared to the reflective area. So if you see in the image, the reflective panels take up a lot more area than the structure itself. So that's a huge benefit, cuts down on costs, and just overall blueprint design. All right, so first we're going to dive into the structure subsystem. So it's consisted of 3 main components: the main support beam, the cross support beam, which is parallel to the ground, and the support swivel. The support swivel is a custom, it's our most manufactured part. It has multiple holes for the beams, for bushings, for screws and bolts. And so the main support will be driven into the ground and serves to hold the entire assembly. So the main support is going to be driven into the ground about 24 inches, give or take 3 inches of tolerance there. And that's strong enough to hold it, to support against wind, against any kind of drag that the assembly will see. The cross support will hold the reflective panels in place as they rotate on the elevation axis. So as if like the sun is rising up on the horizon, the cross support will help guide the reflective panels in that axis. There's a flat on the cross support so that it's not the panels aren't sliding around. So it keeps them in place, keeps them parallel so that it can get an effective reflection and direction into the receiver. And like I said, the support swivel holds the cross support in place as it rotates on the azimuth axis. And after conducting a lot of material analysis with Ashby plots and various other analyses, we determined that 6061 T6 aluminum would be the best material due to its cheap economy, its corrosive resistance, and its overall strength. All right, so this is what I was talking about. The most manufactured part of our assembly is the support swivel. So you can see where the bushing is the crossbeam will go inside that as well. So those are all interference fits so that it stays in place. The 2 smaller holes to the left of that bushing is for the motor mounting bracket, and this hole on right below the bushing is for the wiring for the electronics. And we decided to go with PTFE bushings due to its low friction, its high UV resistance, and high water resistance. So that, and also it contributes to the low maintenance in our design. And this is the crucial piece of our design that allows it to rotate in two directions, 2 axes.
Cool. So yeah, I guess the primary structural analysis that had to be done for the structure was going to primarily be this main support structure, this aluminum tubing that supports the entire concept, or I guess the entire design. So I cut off the support beam here where it goes into the ground, just because otherwise it's too long. But just know that there's another 2 feet of support going down into the ground. However, you can see in this picture, there's about 26 inches above the ground of support. So we're going to get some significant bending stresses there due to any drag forces from the wind. So seeing that, we realized this was our primary design criteria, was that this support structure was not going to fail in high winds. So the way we verified this was applying a wind load, which would be evenly distributed across the mirror panel, and then applying that as a point load in the center, just to simplify the calculations, because if it's uniformly distributed above and below the center line, then we can just apply it as a point load for the purposes of this beam analysis here. So then we can just model this as a simple cantilever beam. And so with the 903 Newton wind load, overall, that's for both panels, 1 meter squared of total area. We have, we can calculate our bending moment, our maximum bending moment down here at the base, which you can see in the free body diagram, and then calculate the bending stress. So you're gonna have to bear with these mixing units here. I apologize for that. But we find that our maximum bending stress at 80 miles per hour wind speed is approximately 115 megapascals, which yields a factor of safety from a yield stress perspective of 2.1 approximately, which is greater than our goal of 2.0. So this is in sort of the, oh, I just got a notice that you guys can now see my screen. Were you not able to before this?
Sorry, I think I got kicked and rejoined.
Okay. So where was I? Okay, yeah. So at 80 miles per hour in the maximum drag configuration, that is the mirror straight up and down, our structure has a factor of safety 2. So this could be repeated. In fact, it was repeated for the cross support. We didn't show it here because it's the same thing over again, and the factor of safety is just greater because there's actually less bending load because it's a shorter structure, support structure. And then the other thing is that this design should never actually see these loads, because above approximately 20 miles per hour, this design would go into a low drag configuration to reduce the loads. Just because beyond 20 miles per hour, you'll see later that the actual motors have trouble rotating the mirrors. So that being said, that was the primary structural design done for the support structure. So go ahead and move on, if Zoom will let me. Cool. Articulation.
Yeah, our next subsystem is the articulation subsystem. Obviously, this subsystem is responsible for articulating our design on 2 axes. Could I get the next slide? Maybe. Cool. Yeah, so responsible for tracking the sun on 2 axes. We used NEMA 23 stepper motors driving a timer belt assembly that directly drives the the azimuth motor drives the swivel, and the elevation motor drives the cross beam support. And it's the same motor timing belt assembly for both the azimuth and the elevation axes, in aligned with our Hedgehog to reduce unique part count. Next slide. Yep. So our NEMA 23 stepper motors are IP55 enclosure rate, have an IP55 enclosure rating. This means they're resistant to both solid dust ingress as well as liquid water ingress. The timing belts are neoprene, which are UV resistant and will withstand the elements well. We used trapezoidal tooth timing belts because they require low to function. So after a long time of use, even with the belts loosening, they still should function just fine. As far as deciding on how to track the sun, there's several different axes we could have chosen to articulate on. For instance, like a spinning elevation, a polar elevation, or I'm sure many of the other designs use a tip tilt axis design. We decided on an azimuth elevation axis because it synergized the best with our simple structure design. Obviously, our structure design is fairly straightforward, and azimuth elevation lent itself very nicely to that. As well, azimuth elevation tracking makes it so that the corners of the mirrors never face down, so we can reduce shading area by making the height of the entire module shorter. Yeah.
We conducted wind load analysis to see at what point our motors can no longer operate and we need to go into our protective mode for high winds. So we did this by treating the reflective surfaces as flat plate airfoils and calculating the load and drag forces caused by the wind. We determined that the maximum lift and drag forces would occur at 15 degrees. Our reflective surfaces rotate past that, but once you go past 15 degrees, you get some separation of flow, and then the lift force decreases drastically. And the lift and drag forces, they act on the center of pressure. For a flat plate, the center of pressure occurs a quarter of the way of the chord length. And then so we use these formulas to calculate the lift and drag. And then use those to get the resultant force between the two forces of 8.77 newtons. And then this force generates a torque on the crossbeam of 2.02 Newton meters. Because there are two reflective surfaces, we multiplied this by 2. So the wind force generates a torque on the reflective surfaces and on the crossbeam of 4.04 Newton meters. And our NEMA 23 stepper motors have a holding torque rating of 2.8 Newton meters. And then our pulley system has a gear ratio of 1.7. So that gives us a total motor holding torque of 4.76 Newton meters, which is higher than the torque generated by 20 mile per hour winds. So we can operate in 20 mile per hour winds, but anything higher, we're going to need to go into our protective mode, which is rotating the reflective surfaces perpendicular to the ground and rotating the main support so that the reflective surfaces are oriented in the direction of the wind. And then so we'll be able to operate year round, with the windiest part of the year in Las Vegas being from March 13th to July 11th. And the average wind speed in this time period is 8.1 miles per hour. So we can operate well above this and expect to be able to generate power year round. Next slide, please.
Quick clarification. I think you said perpendicular to the ground for the reflective surfaces when you meant parallel.
Oh, yeah.
Sorry, just quick clarification.
Sorry, thank you. All right. And then this is our control system that controls the motors for our articulation system. We have one of these control boxes controls 4 of our modules. And this supports our Hedgehog concept of simplifying the design, reducing the overall part count. And this also reduces the cost per meter squared. Our control system box is going to be made out of injection molded ABS or polycarbonate plastic. And then housed inside each box is our AC/DC converter, our stepper motor drivers, which enhance the resolution of the motors, and then the 5 Raspberry Pi controllers, our voltage converter, and then we have 2 grommets on the wiring holes to prevent any water from getting into our box or dust. And then we have a cooling fan as well as a dust screen also to protect the contents of the box. And then we have the sealing gasket also to help weatherproof the box.
So we did a analysis to ensure that our box won't overheat with the electronics in it. Again, we have the fan moving air, and we have a vent on the opposite side of the box, allowing airflow through the box. We use the highest temperature you'll see in Las Vegas, 47 degrees Celsius, and did use conservation of energy to determine the temperature of the box. You can see we expect it to, at the highest temperatures in Las Vegas, to reach about 48.4 degrees Celsius, which is well below the operating temperatures of all of the electronics housed inside.
Oh no, sorry guys, my mouse just died. So I'll have to do this with my clicker thing.
All right. So my name's William Geiger, and I will be covering the optics subsystem. I want to apologize if you can hear the rain around me. I am on my back porch. But the optics subsystem, what it's supposed to be covering is, as the main reflective surface, it's supposed to be focusing mostly on the efficiency of this system, the power generated within the system, and a lot of the calculations also have to deal with the total field layout that was used, the height of the tower, as well as the material that we used. Next slide. So starting with the basics, how does our optics system within the module work? It is based of a reflective film called 3M Solar Mirror Film 1100, and it boasts a reflectivity value of 0.94. And the great thing about this is we've looked at several studies around this, and the reflectivity values do not degrade over a significant period of time, longer than the 20 years of our lifetime that we were looking for. And really the main concern when it comes to this would be making sure that the film is does not peel up from the mirror. We've looked into that as well. The film is going to be laminated onto an aluminum surface, and the aluminum is painted as well to make sure that the adhesive sticks nicely. And on top of that, the edges are taped along with caulked as well, and they can be recocked over years if necessary to make sure that the edges do stick to the sides. This design is meant to be lighter and cheaper than the use of traditional mirrors, and we'll actually look at a little bit more into that on the next slide. So when we were looking into how we should design a reflective surface, the three major factors that we were looking at were the cost of the reflective surface, the overall weight, because that's going to rely on which motors we end up using in articulation, and the durability as well as what we were looking at. So when comparing using a film with using mirrors, the most obvious thing that we can look at is its durability. Glass mirrors, especially in the middle of Nevada, where you could have a dust storm that kicks up, or really any number of other factors that could happen, it's going to be very expensive to replace those mirrors if they are damaged. Whereas a solar film, like especially a cheap one, boasts the fact that it's more protected from the elements, because if something were to hit it, the worst that could happen is it might tear a little bit, but the good news is that with these films, we can actually relaminate right over the old films, especially with the cheap price they're at. As you can see from the numbers that I have present, it's about a tenth of the price, really. On top of that, they're just easily replaceable. They're more durable. I think I've said this already. So it was a pretty obvious choice to go with the solar films over the glass mirrors. Moving on. So the other calculations that had to be done when it came to the optics subsystem were making sure that we reached the goal of producing 1 megawatt for an entire field area and reducing as much shading as we could and making sure that we were efficient in everything we did. So the first thing that we had to figure out is what was the best layout for us to choose. And we ended up choosing the radial staggered layout in a north-facing 90-degree field. The reason why we chose a north field compared to a full circle is that we wanted to reduce the amount of shading from things such as the tower or when the sun's planted in the east or the west, intermodule shading, because that's definitely a lot higher when the modules are in the east and the west. And because we're on the northern hemisphere, the sun, it's just the most efficient. Can you go back? Okay, perfect. It's the most efficient when we're in the north field, so it's going to be facing 45 degrees east of north and 45 degrees west of north. We have a 1.6 meter spacing between modules, and we have a 4.5 spacing between rows, and that is to allow vehicle transport, so that way we can clean these reflective surfaces every so often to make sure that they're getting the most out of it. The reason why we chose the radial staggered, I almost forgot about this, is we did look at several studies, and most importantly, we're looking at the shading and blocking effect between modules within these layouts. And the shading and blocking calculations are extremely complicated. They're geometrical calculations that have to be done at individual times of the day. So instead, what we did is we looked at some other extensive studies that showed that they got blocking coefficients for around, I believe, 100 modules within different rows. And the blocking coefficient was much higher for the radial staggered compared to a rectangular cornfield, which we're looking at as well. And a higher blocking coefficient means more of the rays are actually reaching the tower, which was what we were looking for. So that's why we went with that layout for sure. If you can move on to the next slide. So about our field specifically. So we did some calculations to determine how many modules we would need, the radial distance that we were looking for, and the total field area. And what we came out to was about 1,684 modules. We were looking at the customer need of reaching at least 60% efficiency or 40% of losses. So we took that into account into our calculations, and we wanted to make sure that if that is the maximum we are going to hit, we are going to still hit the 1 megawatt of power. So that came out to about 1,666 modules, and we rounded it up based on how many, based on the rows that we had. The way that we calculated the number of modules as well is we took the distance of each row, calculated the arc length of that, and then basically rounded up the number of how many modules we could fit within that row, which is also why we came to the 169 maximum radial distance. We realized that is a little bit farther than what was desired for this project, but the calculations showed that the atmospheric attenuation losses were not significant until you reached 1,000 meters, and that the total field area is actually reduced from using a full circular field layout of around 100 meters. So not only are we reducing the size of the field, but we're still retaining the amount of efficiency that we're looking for and power generated. And this was all calculated with a receiver height of around 100 meters and intermodule spacing of about 1.6 meters, which is still plenty of spacing to even add an extra module between there. Not that we would do that, because that would add shading. But even so, there's plenty of room for them to articulate and plenty of room for vehicles to pass through. Next slide. So another calculation we did to show the efficiency and the accuracy of these modules is we were looking at the tower receiver size. And we were looking at the customer needs and looking at the assumption of half a degree of tracking error was assumed to be reasonable. And what we did is we looked at the sun at the winter solstice, which was the part of the year where we would assume the least amount of efficiency that we could get. And we looked at the solar angle 15 degrees in the sky, which is when the modules would start producing a lot of their power throughout the day, from about 15 degrees when it rises to about 15 degrees when it sets. And what we did is we did a calculation of where the sun, like the angle that the heliostat would have to be at in order to make the reflection hit the tower. And then we moved that that tracking degree, half a degree in both the elevation and the azimuth angle. And we were able to determine how far off we would actually be if we were to have half a degree tracking area. That ended up being about 0.3 meters. We would determine this trigonometrically. And because of that calculation, we were able to determine a receiver size of about 1.66 meters squared, which even if with the amount of modules we have, should still have the 1,000 suns concentration that we're looking for.
Cool. So we're going to go into sort of the analysis of the mirror backing plate. So the idea here is that we want to stay within that half a degree of deflection to minimize our optical losses in the wind. So we used operating wind speed of 20 miles per hour, which we discussed earlier with the motors. And so we want our maximum deflection in the mirror to be around 4.4 millimeters. And then structurally, we also want to make sure that our mirror backing plate doesn't, I'm calling it a mirror just for brevity, it's not actually like a mirror. Our mirror backing plate doesn't yield under this 20 mile per hour wind load. So for a 6061 aluminum sheet, this corresponds to a maximum equivalent stress of 48 megapascals. So how we're going to go through this is initially we can calculate the distributed wind load on each panel, and then we can estimate bending deflection and stress with hand calculations. And then to get sort of a better idea of the deflection and stress distribution over the plate, we can create a finite element model to compare with our hand calculations, and then hopefully get a better idea of some of the non-uniaxial sort of deflection that we're going to see here. So starting out the hand calculations, little free body diagram on the right, you see that our distributed wind load generates around 27 newtons over the 1/2 square meter panel. And so if we assume, and this is an assumption that we are making, not 100% accurate, but should be fairly good. We're assuming that the pressure is uniformly distributed over the plate. And so that corresponds to an average pressure of 54 pascals over the plate. And so using this, we can model the plate initially as a cantilever beam. So these edge flanges here add significant stiffness to the plate. So we need to account for these edge flanges using the area moment of inertia of the plate. And so if we model this as a cantilevered beam, we're modeling the top half of the plate as a cantilever beam because it is supported in the center by that crossbeam support. And we get a linear load intensity here, which is sort of what we're after for cantilever beam deflection, of 27 newton meters times this 1/2 meter of width that this plate is. And so we get a linear load concentration of 27 newtons per meter. That's from the 54 pascals times the 1/2 meter width. And then this corresponds to a maximum deflection of around 3.1 millimeters. So this is within our goal of 4.4 millimeters from the previous slide. However, we're going to see later that this is not the maximum deflection in this plate because we get higher deflection over in the corner since the support beam doesn't actually go all the way across the plate. And then our maximum bending stress in the top of the edge flange here, if we calculate that using bending stress equation, we see we're around 20 megapascals. So that yields a factor of safety of around 11.9, which is much greater than our goal of 5. So far, all of our structural requirements have been met for this mirror backing plate. So now we can go ahead and create a finite element model. So in ANSYS, I went ahead and made a nonlinear model of this situation. So nonlinear in the sense that all of the contacts are frictional, aside from the bolt into the rivet nut. That's bonded to model like sort of the threaded situation that's occurring there. And so bolt retention of around 3,000 newtons was used for the 1032 fasteners into the rivet nuts. Friction coefficient of 1 for aluminum on aluminum. And then, as I mentioned, the bolt is bonded into the rivet nut, and a 54 Pascal uniform pressure was applied to the front of the plate. This was an assumption we made in the initial calculation, so we're going to continue making it here in the model. And you can just see a couple pictures of the setup here. And then some results from the finite element analysis. We see in the center of the plate, our maximum deflection here is around 3.04 millimeters, which is very close to our hand calculations. The reason I chose the center of the plate is because near the flanges, you get these sort of edge effects where you get added stiffness from being closer to the flange. So I use the center of the plate since that most closely corresponds to the hand calculations, just to check the model itself. And our maximum bending stress here is around 18 megapascals. There's a higher error there just because the stress distribution isn't the same way it was in the hand calculations we did. There's some different effects going on here. And so our maximum deflection up in the top right corner is around 4.2 millimeters, which corresponds to an angle of ½ degree. And then our maximum stress is this stress concentration right here where the support beam ends, and you can see that fairly well. It's around 26.7 megapascals, which still yields a factor of safety of around 9. So all our structural goals were achieved here.
All right, so to pick out some key features about our design, one of them being the pulley system that was shown off in the articulation system. The great part about this is that compared to something like a gear train, it is cheaper, it has a great lifetime, it's solar resistant, and it reduces the cost quite a bit. And then another key feature of our design is the solar film, which boasts a high reflectivity value compared to some mirrors, and it's also relatively inexpensive compared to those same products.
So here's our cost rundown. For the bulk module production, we fairly closely approached the $100 goal given by the customer, the $100 per square meter of reflectivity area, which is one module. As you can see, the prototype cost and bulk cost are significantly different. However, this is purely calculated from reduced shipping costs and reduced waste from the raw materials purchased. So none of the prices, except for the film, which we negotiated with the manufacturer of the solar film, none of the other prices were reduced for the bulk cost, which it's fair to assume that given the modules were in our solar field, it's reasonable to assume that we would get some kind of discount on the other parts, which could potentially put us below the $100 per module customer need.
All right, so in conclusion, our design addresses all the customer needs that were given to us. It's a very simple design, and we made it easy to manufacture, assemble, maintain, and control. And with that being said, we hope our design appealed to you guys, and we would like to open it up to any questions that you guys might have. Also, we'd like to thank our sponsors. Yes.
Awesome. Yeah. Please ask questions. We can jump around the slides as well.
Okay, and good timing. That was right at 35 minutes, just a tad below. So we've got about 10 minutes left in the session for questions and technical discourse with the panel.
All right, I have a question. I know Thomas didn't need to go first. Please take the floor. This is one of the first slides. There was on the PTFE bushing that went through the vertical pipe member. That one, yes. So, did you consider the fact that it has zero support in the middle because of the hollow tube, and it's going to get edge loading pretty heavily?
Yeah, so yeah, definitely looked at that a little bit. So these bushings are rated to, I believe, I can't remember off the top of my head, but I remember it was significantly rated significantly above the actual loads that this structure sees. So definitely looked at that, but wasn't too concerned with it because it was so overbuilt, to put it one way, if that makes sense.
Yeah, so I was kind of curious as to if you considered the fact that it wasn't supported on the entire outside, but it's basically circular.
Yeah, we essentially just took that into account by making sure the bushing was rated well above any load it would actually see.
Okay. The second question I had was around the fan. Is there a film on the intake or the?
On the intake, we have this sort of, I don't really know how to describe it, this cover over the actual slits here. You can sort of see one of the slits, and there's this cover going around it. And then I think this is actually maybe an old render because there's a dust screen that like goes underneath this flange here.
And there's also one on the back of the fan, right?
Yeah, there's a dust screen here as well at the outlet to prevent any ingress.
Okay. Okay. Yeah, I figured there was one on the fan side that's standard, but I just wanted to make sure you didn't let the dust into your.
Yep.
All right, and then I had a big thumbs up here on the mirror material selection comparison. It was pretty neat how you actually showed other considerations that you had chosen not to go. So kudos for that. Thank you.
Thank you.
Yeah, that's fine. Yep.
I'm sorry, I'm having trouble hearing you. Do you mind repeating the question?
Oh, it wasn't a question. It was just I like the fact that you compared the different options here, even the ones you didn't go with in the end.
Oh, thank you.
Cool.
That's it for me.
Awesome. Thank you.
So back on the control box slide. So where is this control box located? Because you say one control box controls every 4 modules. So where is it located exactly?
So it would be underneath one of the modules, obviously preferably in the center of the floor it's controlling. And that's just so that we can make sure it's being shaded to prevent any like added maybe radiation, adding heat to the box.
Okay, so I guess I'm having a tough time picturing how the wiring connecting this control box to the other 3 modules that it would also be controlling is working.
Not quite sure what you mean. So we have one cable exit here, which could then be split into a few more cables. So it would be 4 cables going out, 1 to each module, controlling each motor. If that makes sense.
Yeah, so could you go up to like your overall design picture, I guess. Maybe I'm not being clear, so I just want to make sure I'm clear with.
Yeah, let me find sort of like our fullest picture here.
Right, so where is this control box located?
Right, so I guess this is sort of like an artifact of this mirror being here. It's literally like right under this mirror.
Okay.
And it's
All
on
right.
the ground if that.
Yeah, it's on the
Grace
ground
it
right
up.
underneath this mirror.
Okay. And sorry, can you go back to the box one more time?
Yeah, definitely.
Slide 7 has a good image of the full layout if you're looking for one.
Yeah.
Oh yeah, here we go. This is just the free body diagram though. The box isn't here. It sits like right underneath where this mirror is.
Okay. Anytime you tell me that something's sitting on the ground, I worry about how you're going to protect that from the environment, intrusion of rain, and those sort of elements.
Understandable. So our sort of thought process there was that it is like on the ground. However, there's no seals until you get about 4 inches above the ground, above the bottom of the part. So
Okay.
that was sort of our thought process there.
Okay, and then my other question, I enjoyed the material selection breakdown as well, but one of the things that y'all mentioned was that you chose it because it could you could easily replace the solar film over time. Do you have an idea of how that film degrades over time? Is that going to be a concern from a maintenance issue?
No, at least with the reflectivity, we've shown that we found data that suggests that the film degrades for about, I think, 3% reflectivity over the course of 20 years. So in terms of its functionality, we're not concerned with within the lifetime it degrading at all. The only concern mentioned earlier was the possibility of it peeling up around the edges, which the process again of applying it would be a lamination process over the aluminum plate, and then we would cover it with tape on the edges and also caulk it around the edges, just touching up anywhere where we see it might be coming up and we didn't perfectly laminate it. And the idea is, in order to make sure that it would stay over those 20 years, is that we would have maintenance done basically whenever it's being cleaned and washed. We would have them check along the edges to make sure it's not coming up, and if necessary, re-caulk the edges. And if the film is damaged, that's when we would get into the fact of, if it is damaged, we can relaminate directly over it. And that's what that information was for.
Right.
Okay.
And that's another aspect of sort of like going into that protective mode, is that we're protecting the mirrors from any debris and the high winds.
Okay. And then the final thing, and then I'll let Tom take over, is the module cost. So again, the customer was shooting for $100. Y'all get close when it comes to production, and I agree you could probably drive that down. I think there's a couple of resources you could probably just Google in order to justify driving that cost down more than you actually did. But one of the things I started thinking about is the customer. So while they seem to be focused on module cost, I've set through 6 designs, and depending on how you lay out your field, you have quite a number of modules to meet your power requirement. Did the customer give any indication as to a total cost metric that they were shooting for?
No, they did not give a total cost metric. They gave a power production like metric. They wanted 1 megawatt of power, and they also said they want a concentration of about 1,000 zones. So that's what we went off of.
Yeah. So I just think when you talk to your customer, right, while they might not mention it, if you think about how the different variability of overall cost across the 6 groups, you might have a group that has a $200 per module cost, but then their overall cost ends up being half of what y'all's is because of the number in order to reach that power requirement. So while the customer might not mention it as a requirement, I guarantee you they have some sort of dollar value in mind that they're trying to hit.
All right,
But
thank
other
you for
than
that
that, great
suggestion.
presentation, guys.
Thank you very much. So in the future, we will definitely consider overall cost, and that's extremely important. But I think our mentality was that since there were so many specific parameters to be met, like the 1 meter squared per module and the power requirement, we kind of thought everyone would be around the same ballpark depending on their module cost. And we were very suspicious on some of these, some of the numbers of total modules needed in design. Some I think we saw a group that only needed like 400, and we were just really curious on how they would meet the power requirement.
Yeah, I had similar thoughts.
And thank you again for your suggestion.
All right, so I'll jump in and I'll start. I don't often do this. I'll start by talking about things I like. I was talking with Rick on instant message, and you guys, I think, are the only teams that said, "Hey, here's what our factor of safety target is." And I was going to ask, where does that derive from? I think I saw a factor of safety of 2 on yield at one point, and then a factor of safety on 5 on yield at another point. Did that derive from discussions with the customer, or did you kind of pluck those from comparisons with similar systems, or where does that come from?
So the factor of safety 2 was on this beam here. And I chose that myself as a fairly low factor of safety, just because this design should never be put in this situation. So this is like an extreme worst case scenario. So in that case, I decided that factor of safety 2 was probably sufficient, just because of the fact that like this will never actually happen, and we're overbuilding our system anyways. So we want to make sure that it's not like we're not choosing too large of a main support and adding cost. And then the factor of safety 5 on the mirrors, this was a more, this actually sort of corresponds to like a similar like overall safety, I don't know how to say it, safety consideration, because our wind speeds here are lower, wind speeds we would actually see without going into protective mode. And so the factor of safety 5 there was just sort of a standard catch-all, like this is a large factor of safety because we're not designing for actual like structural safety here. We're mostly designing for deflection, and this is just to make sure that we're not like leaving out the actual like failure of the panel, if that makes sense.
Yeah. So I appreciate you put some thought into what those factors should be, and you know, taking into account various considerations. I really appreciate that. Other teams were saying, well, this is what our factor of safety is, and okay, well that's great, but what should it be? And so you guys did that, so I really appreciate that. I appreciate you gave some thought to the compliance of your system and how that affects aiming. I like that you know, you've got film on a flat panel, and you recognize, well, you know, flat panel isn't very stiff, so you've got stiffeners added to the edge of that. That shows some good thought. I will pick at a FEM. I think a FEM, especially a nonlinear FEM with contact and bolts and whatnot, all modeled, is way overkill for what you were doing. I think it would be probably more than sufficient to do a hand calc there. And I guess I would wonder, you're talking about the you know, the angular deflection of your flat plate, and I guess that corresponds with a change in the, I guess, the normal direction of the reflection. But it seems like the angle, the change in the angle of the actual rays is going to be double that, I think. I'm not 100% sure, because it's been a while since I've drawn rays on a sheet of paper and you know, traced you know, paths of light rays, but I think it might be double what you're expecting. So I think you might be over what's required. But I do appreciate that you're considering that. I would also encourage you to take into account the overall compliance of the rest of your structure, because, you know, as the wind's blowing, the panels are probably going to have the most motion, but they might not be all of the motion that's important to consider. I'd think about the motors and, you know, potential like backlash in the system, being able to change the angle that things are being reflected at. Let's see what else I have. Your layout. You seem to indicate that your cleaning vehicle is going to be like weaving around your modules. Is that going to be something that your customer is okay with?
We expect them to go between the rows to clean each row at a time. They're not expected to weave between here. I don't know if Who is control of the mouse right now? Is that Shane? Yeah.
Yeah.
Clicking the layout.
So you expect them to go on basically like a constant curvature arc through the layout?
Yeah. Between each row, we expect them to drive through like a curved road, essentially. And we did allow them to have an extra meter of spacing. I believe standard U.S. highway size is 3.5 meters, and we accounted for 4.5 meters between rows. And that also accounts for if the planes were perfectly horizontal as well. I'm sorry, if the mirrors were perfectly, so their normal was straight up. And obviously when you're cleaning them, it's probably going to be at night, and it's also probably going to be perfectly vertical to allow the water to come off them, or at least at an angle. So with all that accounted for, the car should have more than enough room to go ahead and get in there and clean them, as long as they're driving between each row and not directly outwards from the tower.
Yeah. Okay.
Yeah,
let me
just to
ask, how
clarify.
are they actually cleaning these guys? Is it a water spray?
Yeah, just water.
And I think I saw 500 psi water spray.
Yeah.
What's 500 psi going to do when it hits your flat plate?
Was it 500 psi? I don't think I saw that specific number anywhere in the customer needs.
No, he's talking about.
I might be pulling that from other groups.
Okay, I never
Wait.
saw that customer need.
Can you say that again, William? You cut out.
I think he was talking about what that would do to the actual film.
Right, but I never saw the 500 psi customer need.
Yeah, I might be pulling that from other groups. So I guess I would ask, like, what pressure do you expect them to be spraying your panels with?
That wasn't really thought of. I'd have to look at the data sheet for the material itself to determine what pressure would be acceptable. But I believe the customer need was just the fact that the surfaces were washable. I believe some of the other groups quantified that into a pressure metric. We did not do that, but we do have the data sheet, so we can look at that and determine the appropriate pressure.
Okay. Yeah, you might want to do that.
Yeah.
Yeah, because that's something with a flat plate. It's something that seems like, you know, you could potentially dent your plate, and that would affect the line that you're reflecting sunlight onto. So I'd be a little bit concerned about that. How is your that flat plate? How is that attached to the crossbar?
So
is that like U-bolts and?
So we originally had U-bolts. We decided that the U-bolt plate actually shades the mirror a bit. I don't know if I have a good picture. I think I do have a good picture of it. So we actually made a custom U bracket, and then we have rivet nuts that go through from the backside and are screwed in around this U bracket here. And that's just to reduce the shading from the actual U-bolt here. And it's also a bit cleaner and easier to install.
And so what I'm looking at here, I'm not seeing those stiffing angles. Is that are those going the other direction there?
So the edge flanges are right here. It's kind of tough to see.
Okay, so they stick up away from that crossbar?
Right. And the reason is that we didn't want to have to put a slot in the crossbar here.
Yeah.
Bad design.
Okay.
And yeah, to clarify on this one, these modules aren't here in our design. If that makes sense.
Oh, okay.
So this
yeah,
is
okay, yeah, that helps.
For a vehicle to go through.
Got it. Let's see. You said that you would safe in 20-mile-an-hour winds, so you'd rotate the mirror basically parallel to the ground at that point. How often do you expect to see winds above 20 miles per hour?
So I think, like Noah said, the windiest part of the year is in March, and the average is like 8 miles per hour. So
okay, but wind isn't like an average phenomenon, right? I mean, you've got variability from day to day. You've got variability from minute to minute, right? Are we saying that if we've got 20-mile-an-hour winds as like a steady state thing that now we have to safe, or are we talking about, well, if we've got 10-mile-an-hour winds, we could have a gust to 20 miles an hour, and so we've got to safe in 10 miles an hour? Statistically, what's the what are we talking about here, and what does that do to the uptime of your system?
Yeah, no, it's a steady state thing. And so the reason is that simply if the wind, like if there's a gust over 20 miles per hour, say, the only negative impact that could have is just to sort of knock off the tracking a little bit. And then these stepper motors have closed loop control. So the driver would know that it's been sort of like backstepped, if that makes sense. And it would just return it to its previous position when the wind dies down after the gust. So if that, I don't know if that makes sense, but then if the steady state winds are over 20 miles per hour, odds are it's a cloudy day anyways. So we're not going to be producing much power to begin with.
Additionally, we
Okay.
could look into how frequently the steady state of at least 20 miles per hour winds occur, but we don't have the exact like yearly estimate.
Yeah, I would recommend doing that, just, you know, as a measure of uptime. I don't know that it's a true statement that wind speeds would correspond with cloudiness. Maybe it is, but I'm not convinced of that. The other thing I would say is you, again, going back to your factors of safety, you said, all right, here's our factor of safety targets, and here's how we meet them in a, you know, 20 mile an hour wind situation. But again, if you're saying that's a 20 mile an hour steady state wind, there's going to be some amount of gustiness over top of that, right? So if you're saying we're not going to safe until we hit 20 miles an hour steady state, what gust is that going to correspond to? And now that becomes your design load case. So there's a whole set of statistics, and I'm sure, you know, if you go over to your meteorology department, you can ask a professor over there, hey, what does this look like? How do we do that analysis? I would recommend doing that, because that's something that is going to impact your loading.
Okay, yeah, that's very true. It makes a lot of sense. Definitely something to look into. Thanks.
Okay. I see Dr. Trump said we're 10 minutes over. I don't know how long ago he said that.
Oh
so.
man.
Yeah, no, sorry, I didn't want to stop things because you know there was a nice, you know, kind of back and forth discourse and technical discussion, so I didn't want to stop it. But yeah, we're almost at an hour now in terms of a 45-minute session. So I'm happy to kind of let things continue going, but I myself have to leave because I have to give a final exam in less than an hour. But maybe I could just stop recording there.